did the chain rule first. But I think it's just really good practice to see as many of these as possible. So here we go. So I'm going to do number 40, and I'm going to do the derivative chain rule. So chain rule, and you have, this is the biggest part of this written assignment, is that you're practicing the chain rule, because the more confident you are at the chain rule, being able to reverse it to go backwards, you should get more and more confidence with that. Okay, based on what the chain rule is. So the chain rule for this one, number 40, would be that y prime is what? So we're going to do the rate of change in the big picture, which is 1 over 1 plus that thing squared. That's arctangent, right? Then times the derivative of the interior function, which would be negative 6x to the negative 7. Okay, so whenever you find a derivative in closed form, you also found something else. Okay, so not only did we find that the rate of change function for this function is what I wrote here, but now we also know that if you have a net accumulation function like this, we know what the closed form version of this net accumulation function is because of what we did, right? So knowing that the rate of change of this function is this one, we also know something else. We also know if we have an open form net accumulation function like this, we know what its closed form is. What's its closed form accumulation? What's the closed form version of this? Well, it's the antiderivative of this, which is arctan of x to the t, so we'll do t to the negative 6, and that from a to x. And so what we're working on now, right now in the course, is given open form, given this rate function, can you reverse the chain rule, go backwards, and do that? And so we're just, in this section, we're just practicing the chain rule and practicing writing the open form and the closed form.
For that last part, for the closed form, would it be, oh wait, never mind. You're doing it now.
Okay, and then this is our plus c, right? So this whole thing is our plus c. Okay, so this is part A for this homework, and then this is B, and then this is part C. Okay, any questions on that?
I have just one.
Sure.
So I wrote the net accumulation of the rate that you had there in part B. But for part C, I only wrote the arctan x to the negative 6 minus arctan 8.
Yeah, that's fine. That's fine. This is just to just break it up into separate steps. This is the answer.
All right, thank you.
Professor, I just had one question about a certain format. There were a few questions which had a as a constant in the problem. So obviously that's a constant, but when I was writing for part C, I didn't substitute that a, which was a constant, if that makes sense. So it was like, let's say, the constant and then a to the power of negative 6. Is that going to be marked wrong, or will the grader know that a is a constant and the other a is the second thing that we're subtracting from?
Oh yeah, don't worry about that. Yeah, that's not. I wouldn't worry about that. Yeah, that's okay.
Okay, sorry.
Just know that So there's two different a's going on. There's an a you're saying there's an a in the rate function, and we also call this a. Yeah, let's not get that.
Doesn't matter.
You don't have to worry. Don't have to worry.
Thank you so much.
Don't get worked.
For that one, I changed my limits of my integral. Instead of a, I did b. Would that still be okay?
Of course. Okay. There's nothing magical about a. Yeah, that'd be fine.
Thank you.
Okay. All right.
Are we able, I'm sorry, just one more question. Are we able to, for the part B, just have it the open, like we don't have the variable a to x, it's just the blank one? So
yep, sure.
we can do that too.
Mm-hmm.
Awesome.
Okay, so here we go. So let's do one more example of undoing the, so one more example of writing closed form, but given this first, right? So starting with this first, where we didn't take the derivative first to know what the antiderivative was. So, because that's really the goal here. The goal is given a net accumulation function in open form, write it in closed form. So let's do one more example of that. And that's right here. So let's do this one right here. So I have integral v squared plus 1 over square root of v cubed plus 3v plus 4. And so the first thing we want to do is always check to make sure it qualifies. So we'll rewrite it as a product, like we said last time. And we got to make sure it qualifies. So do we have, sorry, that should be dv. So do we have this, where we have the derivative or constant multiple of the derivative of the interior of the other, right? That's what the chain rule is. You take the derivative of the interior. So when you're looking to undo the chain rule, you have to have that qualification met. You have to have the derivative of the interior. Do I have that here? So looking at powers, I've got v cubed and 3v, and then I have v squared and 1. So maybe this is the derivative of that, and we got to check, right? So what is the derivative of this? It's 3v squared plus 3. Now I have v squared plus 1, so is the condition met?
Yeah, they just took the 3 out.
Yeah, so it's actually kind of rigged pretty heavily here. So if you take the 3 out, then you see we just have a constant multiple of that thing, v squared plus 1. So we're good. We have verified that the form is okay. So these exponents have to be perfect. This has to be square. This has to be a constant. But then on both these terms we needed the 3 in order for it to end up being a constant times exactly v squared plus 1, which is what we have. All right, so we're good on that. And so now we're ready to, oops, back. Still want that. All right, so I'm going to erase this. Okay, so here we go. So now what do we do? So now that we're going to write the antiderivative, so this was the derivative of this that popped out in the chain rule. So we're going to do the antiderivative on this one, right? This is our g prime of f. And what's the antiderivative? Well, we're going to raise power on that. So our first attempt is going to be v cubed plus 3v plus 4 to the positive 1/2. Okay, and so so the goal here is not that we have to every time do a derivative and check it and then make a second attempt. So as you work on more and more of these, the goal is that you can just get it right on the first attempt. So let's imagine taking the derivative of this, and what are we going to need so that our derivative would be just like this? So first of all, we've got this 1/2, so that means we're going to need what? 2, right? So because we don't have a 2 here, 1/2 times 2 makes that 1/2 go away. And then also, we take the derivative, we're going to go at 3v cubed plus 3. So we're going to have an extra 3 that we don't have here. So what do we need? 1/3. Done. So that's the goal, that you can do it without, the goal is you can do it without taking the derivative, comparing it, and then doing a second attempt. That you can see, oh, we got to take care of the 1/2. There's no 1/2 here. So I need a 2. Then I need to take care of the 3, because I can have a 3v squared plus 3 when I take the derivative of the inside. I don't have a 3. So I need a 1/3 to take care of that. And then I got it. And I just saved myself lots of time over U substitution. Okay, lots of time and lots of writing. Okay, did I lose you? So that's the goal. The way that I just did that problem right now is the final goal of this kind of structure that I'm giving you with first attempt, take the derivative, compare it. Second attempt is right. So anybody have a question on that?
So then to check if you're right, you would just find the derivative
Always, yeah.
of the 2 times 1/3 times
That's right.
1/3. Okay.
Yeah, you can always take the derivative. That's right. Another way to check it is in GC, so we've got this form and we've got this form. Which one would we trust in GC? Which one would we trust, the open form or the closed form?
Closed.
But the closed form was just a result of our algebra, and we want to check. This is what we're trying to check. So this is the one we trust because it was the given problem. So we go in GC and you can graph. We know how to graph graph accumulation functions, and we'll need a particular value of a. So you could start at 1 or 0 or something like that, and then you can graph this one, and then you can see if the graphs are the same. So that's another way to check it. But yeah, you can always take the derivative of your answer using the chain rule and compare it to what you started with, and if it's exactly the same, then your closed form is correct. Okay.
Would you do plus C if you were to graph that in GC?
No, you have to have the right plus C, right? Depending on the A that you pick here. So if you do 0, then remember your plus C is minus f of A, right? So
Right,
to get it
okay.
to look the same, then you've got to do this thing at 0. So you're going to
Okay.
evaluate this at 0, and that will be your, so minus this evaluated at 0 will be your plus C. And then they should be exactly the same graph.
Awesome, thank you.
You're welcome. Okay, so let's look at an applied example here and talk about total accumulation. So a culture bacteria in a particular dish has an initial population of 250 cells and grows at this rate, according to this function. All right, I want to write 2 expressions for P. The population T days after the initial measurement in open form and in fully simplified closed form. So how do I write the population at time T days in open form? We've been doing this all semester. And so are we talking about a net accumulation function or a total accumulation function, first of all?
Total accumulation.
Total.
Now this is total, right? So this is total accumulation. We know our total accumulation is going to be what? It's going to be our initial amount, 250, plus the net accumulation starting from 0. In open form, that's our integral. So now we actually want t to be the independent variable of the function, so then I'm going to, instead of using t here, I need to use something else, so I chose u. Okay, so this is familiar, right? Everything from before plus net accumulation of changes in population. Okay, so watch out for, we're not accumulating the rate. We never have accumulated the rate of change. What is it we accumulate? We accumulate small variations in the quantity. This is a small variation in population. That's what we're accumulating. So it's easy to slip into the language of I'm accumulating the rate. You're not accumulating the rate. You're accumulating rate times change in independent, which together, right? That's our MDX. That's a small variation in the quantity. We accumulate small variations in the quantity to find out what the quantity is, right? So that's just a side note there. Don't watch out for saying I'm accumulating the rate of change. You're not. You're accumulating variations in the quantity that are found by rate times dx. In this case, dt. All right, so what are we going to do now? So now it says I want to get fully simplified closed form. So to get closed form, it's about what? We're going to use the fundamental theorem and antiderivative on this. So what do I have? I have 50e to the 0.3u, and I need the antiderivative. So we're getting some practice at this. And we have like a little chain rule here, but pretty easy one because it's just a constant, right? So what's the antiderivative of e to the 0.3u? Well, first of all, it's e to the 0.3u. But we know that by the chain rule, if you took the derivative of that, you'd also have what? You'd also have times 0.3, a times 0.3 that we don't have here. So how do I need to adjust this? My 50, and then also, it's a lot of silence out there, over 0.3.
Sorry, I don't know if you wanted us interrupting.
No, that's okay. Yeah, but so if I ever ask a question and I pause, yes, you can answer. But I just want to make sure that this undoing the chain rule thing is making sense, and we're getting better at it. But so the antiderivative of e to the something is e to the something, right? But if it's a chain rule, then by the derivative of that would have a constant of 0.3, which we don't have. Therefore, I need to divide by 0.3. Okay, and I also have my 50. So there's my antiderivative, and we know we're going to apply it from 0 to t. So let's get the pretty version here. So there's that. Okay, and now I'm going to apply my fundamental theorem of calculus, which says final value minus initial value. Okay, and so what I'm about to talk about in the next 5 or 10 minutes is a really important concept that's on the exam, and the success rate on the exam has been anywhere from 5 to 20% success rate. And so I'm just trying to grab your shoulders here, get your attention. Let's really pay attention to what we're about to talk about, and so you don't miss that. Let's get the success up to 30 and 40% this semester, and you're going to be in the group that's in the 30 or 40%. Okay, so notice we have the 250 constant, and then we're applying on the integral, we're applying the fundamental theorem. And applying the fundamental theorem means what? It means final minus initial. The function evaluated at t minus the function evaluated at 0. But having a 0, and I've mentioned this before, having a 0 as your starting point, does it mean that this term now is 0? Yes or no? Does it have to be 0?
It is not 0.
It is not 0. There are many cases where evaluating a function at 0 does not give 0. It gives a non-zero number. Sometimes 0, like polynomial. If you plug 0 into a monomial. Okay, if you plug 0 into a monomial like x to the 8th, yes, you get 0. But there are many examples of functions where at 0 the function is not 0, and you have to do this. You can't just disregard this. Okay, so that's kind of the first big point here. If you're accumulating starting from 0, you must plug the 0 in and make sure that make sure you're evaluating that correctly, especially if it's a non-zero number. We got to have that. So then, going on from there, notice we had our starting value, right? We had our starting constant, and now we have a non-zero number also over here. So to simplify the closed form, we're going to add those together. Are you hearing me? So notice, in the closed form, there's the open form, there's the closed form. Notice the constant in the closed form is not the starting value. Are you listening? The constant in the closed form is not the initial value in this function, in this example. Now, if I do p of 0, what p of 0 in the open form gives what? P of 0 in open form gives 250 cells. If I do P of 0 in the closed form, what do I get?
250 cells.
Do I get 83.3?
Yeah, that's the constant.
No, you don't get that because e to the 0.3 times 0
Right.
is 1.
Yes. This is the same function in a different form. This is the same function in a different form. So if P of 0 in the open form is 250 cells, then P of 0 in the closed form is 250 cells. And it is. 83.3 plus, this is 1, 166.7 gives the 250.
Where did we get the 83.3 from?
Adding together 250 plus or minus this.
Oh,
This is
okay.
non-zero, right? So these two together are both constants. So when we simplify the closed form, we end up getting 83.3 as a constant. But it's not the function value at 0. The function value at 0 is still 250. So you have to hold on to your constant, evaluate your integral with final minus initial, and then if that initial is non-zero, then you can combine it with this to simplify and get a different constant in the closed form, but it's not the starting value. The starting value is still 250.
So the correct answer would not be that third line. You would want us to simplify it all the way down to that fourth line?
Well, that just would be normal, right? This is still true, but it's, this is much longer and more complicated. So if you have two constants in an expression, it's just normal, conventional to simplify. Add them together.
I feel like I would have just left it at that other one because it just kind of looked like the right form to me.
Well, I mean, which would you prefer to work with? 50 over 0.3 e to the 0 plus 250 or just 83.3?
Yeah.
This is just streamlined. It's more efficient. It's simplified. And it would be kind of abnormal to leave it this way.
So if we were given that t is equal to 0, so to find the p of 0, then would you just times 166.7 e to the 0.3 times 0?
It's the same way you've been evaluating functions your whole life. These are both PT. We have the open form, and now we have the closed form. In the closed form, you can get rapid results. Input in, output out. Input in, output out. So P of 0 is what you get when you evaluate that at 0. And you still get 250, the initial amount. Even though the constant in that function is 83.3.
Okay, thank you.
Yeah. Okay. So the entire quiz today is on this, because we're gonna get a little practice up front, and then you get some more practice in recitation with this idea. So you'll practice again in recitation, practice on the quiz today, and then we're gonna have the highest success ever on the exam, over 20%. Okay. So does it make sense what I'm saying? That in open form you have your constant, which is your initial value. In order to get to closed form, we have to use the fundamental theorem, which means final value of the quantity minus initial value of the quantity. And if that is 0, you have to make sure that that initial value of the quantity is non-zero. If it's non-zero, then you can combine with the 250 to simplify. But then your constant in that function is no longer the initial value. But they're the same function, and they have the same. It's still, the initial value is 250. It's just that that won't show up in this constant here in closed form. Okay, so watch the video again, slow it down, pause it, think about it, make sure we got that. And then, like I said, today's entire quiz is on this right here. So before we move on, any last questions?
So since 250 is the initial value, can we look at like the closed form, because the constant, because we basically changed the constant. even though it's starting from 0, it's still adding on, in a sense, from 0. In this example, at least that's how I would think.
Well, what is the initial value of the? How many cells are there initially according to closed form?
Oh, it's still gosh, I can't speak. It says like there should be, if t is 0, it would be 250 still.
250.
Okay.
250. Yeah. So
All right.
according to the closed form, at t equals 0, there are 250 cells, just like the open form. But it's just that number doesn't show up here. When you evaluate it, you get the 250. So yes, it's the exact same function. This is just the open. These are the exact same function. Graph them on GC, they'll just be right on top of each other. It'll just look like one graph.
So to clarify, the constant c is not always the initial. You're better off just substituting in 0 in the closed form and seeing what value you get, instead of just automatically assuming it's 83.3, is what I'm hearing. Is that correct?
Yes. Yeah. So just because there's a constant doesn't mean, in closed form, doesn't mean that that's the value of the function at 0.
Yeah.
Right.
You're better off substituting 0 to see what value you get in the closed form, like actually substituting and doing the math and just assuming it's 83.
Yeah. If you're trying to find out what the initial value is at t equals 0, then yes, you need to evaluate the function at 0 and make sure.
I have a question. So this happened this time because we had an initial value that we added the whatever we substituted 0 into?
Yeah, this was not this time. You're right. In this function, it happened because this was non-zero.
Right. So if we have a non-zero value, then we know then that's like I don't want to say a red flag, but that's like we should know that the closed form's constant. Because what if on the exam we don't have a calculator to plug in? Oh wait, you let us have calculators, right?
Yeah, you'll have everything you need to if you understand what's going on, you have everything you need to answer the question correctly.
Oh, okay. I don't know why I thought I was going to do this without a calculator. Never mind.
Okay. Yeah, and so if this is 0, so oftentimes also, if you plug in 0, you'll get 0. And if that's the case, then in your closed form, your constant will be the initial value. But it's in those cases where you plug in 0 and you get something other than 0, and you had that initial constant, well, after you combine these now, that's no longer your initial value. That's not P of 0. P of 0 is still the 250. But the added constant will not be P of 0. Okay, so we'll see how we do on the quiz. All right, and let's just take this a step further here. So we represent in 3 different ways the population 10 days after the initial measurement. Okay, so what's one way I could represent what the population is 10 days after the initial measurement? What's one way?
P of 10.
P of 10. Good. What's another way to represent the population 10 days after the initial measurement?
250 plus the integral from 0 to 10, 50e, 0.3u du.
Good. So can I just write RU? Du? So that R is this one. Okay. What's another way I can represent the population? Somebody new?
66.7 E0 to the power of 0.3 times 10 plus 83.3.
Right. Good. So those are all ways to represent what our population of cells would be at 10 days after the initial measurement. And so now we say we want to find the value. We want to find the value. Which one is the ticket to getting the actual value? Exhibit A, B, or C?
The last one.
Yeah, right. Closed form. That's what we said. Our closed form makes getting values readily available. We got lots of inputs, lots of outputs, easy to find. So whatever that is. I don't know if anyone has started punching, but I don't have a calculator in front of me. But so that one would be the one we can use to find the value. All right. Any questions on this applied example? Okay, so we want to move on to the next kind of technique or harder type of antiderivative. So you have lots of practice with the reverse chain rule or undoing the chain rule in your homework for Wednesday. And actually, that's the most probably the most important technique, because it finds its way into these other techniques we're about to do, and it's kind of the most prevalent. It's the one you see the most. So really recognizing when you have a rate of change function that is the result of chain rule, recognizing that, confirming it, and being able to undo it. So lots of practice. And if it's not going well, then get help from us. Come find us in office hours and we'll do practice problems. But if you're not reaching out to us, we're just going to assume that you're picking up on this technique and you're able to do it. Okay? All right, so the next type of harder antiderivative is something of undoing the product rule. And so let's review the product rule. Remember that the product rule says this, that the derivative of a product is the first times the derivative of the second plus the second times the derivative of the first. Okay? Thus, if we applied antiderivative to all three terms, we would have, so we'd be back where we started here, and we'd have the antiderivative of f g prime plus the antiderivative of g f prime. Okay? So in this technique, we're not on the lookout for ones like this. We're not on the lookout for this trying to recover f times g. Okay? That's not what this is about. What this is about is we are given, this is our given integral. This is the one where antiderivative is desired. It's like one term from the product rule. But this is unattainable. This antiderivative is unattainable by the things we know, by known techniques. Okay? So then the strategy then is, if the other term of the product rule is attainable, is doable, well, then we can solve for this indirectly. We can do this instead, and then how would we know what the value of this antiderivative was if we knew this one? What would we do? So I'm trying to find what this equals. I'm able to find what this equals. So then how do I get this one, what this one equals? What would I do? Just one step of algebra.
Subtract from f times g.
Right. So then the one that we're trying to find would just be our product, f times g, minus the one we can do. Right? So it's just algebra. Just kind of subtract it, move it over here. All right, so here's our strategy. We're going to think of our given rate function as one of the terms in the product rule, and from that, we're going to determine what f and g are. Well, f we'll already have. We'll just have to do a little antiderivative to get g from g prime. And then we're going to compute the product fg, and we're going to do this easier antiderivative of gf prime. And then we're going to solve indirectly by just subtracting, right? We're going to take fg minus the easier one. So does that kind of, before we get to an example, does that strategy make sense? All right, so let's try an example here. So again, here's our This is just a recap from the last slide. So here's the one we're going to try. We're going to do the antiderivative of 4x cosine x dx. Okay, and so as we start adding new techniques and adding new approaches to our tool bag, we always want to, when we come to a new antiderivative, the first question we're always going to ask, if it's not a simple one, just a plain rule, was this a chain rule derivative? Was this a chain rule derivative? The one that we're just finished up working on. So yes or no? Is this the result of chain rule 4x
No.
cosine x? Okay, and so as a good kind of practice about this, what one change, what different problem that's very similar to this, what different problem that's very similar to this would be undoing the chain rule?
If it was cosine x squared.
Okay, so he's offering up if this was cosine of x squared. Now this is a different problem. This is a different problem. Would undoing the chain rule apply now?
It could.
Yes.
Yes, right? Yes. Why? Because out here, I have essentially the derivative of this interior part. This would be undoing the chain rule. Okay? So we're going to ask that question a lot. Is it undoing the chain rule? No. What small change would it be then to be undoing the chain rule? Because this really helps you practice, identifying that. Okay, but this is our problem, which is not undoing the chain rule. Okay, which is not. So we know we've got f and g prime. So maybe the 4x is one of those, f or g prime, and then the cosine x is the other. So how do you know? Well, we're just getting started at this. So we kind of just maybe take a guess, right? So just match them up, start working it out, and what's our goal? That this is doable, right? So if we start working this, we pick an f and pick a g prime, and we start working through, and then this is doable, then we made a good choice, right? That's the goal, that this one we can do. All right, so we'll just try. F is 4x and g prime is cosine x. So we'll come over here, do our side work. So f is 4x and g prime is cosine x. And so what do we need? We're going to need g and we're going to need f prime to finish to get this stuff. So what's f prime? That's just 4. What is g? So easy little antiderivative here. That'll be sine.
Sine x.
Sine x. So now,
Shouldn't it be negative?
what's the derivative of sine?
Cos x?
Right.
Oh, never mind.
So we got it, right? Okay. So now we look at g f prime. So I'll come down here and we'll rewrite. So I'll rewrite this now down here. So what's f times g? F times g is 4x sine x. That's my f times g, right? Equals the answer, our original problem, right? So that's the one we're trying to do. We already know what that is. Plus integral of g f prime. So that'd be sine x times f prime is 4 dx. And so now here's the test to see if we picked our f and g prime correctly. Is this attainable? Is it doable?
Yes.
Yeah, 4 sine x. Pretty easy antiderivative. Don't need any special technique. We just recognize that a function whose derivative is 4 sine x. And what is that?
Negative 4 cosine x.
Right. Right, so the 4 just comes along for the ride. The antiderivative of sine x is negative cosine x. And so we've got it. All we have to do is subtract this from both sides, or add 4 cosine x to both sides. So our answer is 4x sine x, and it will end up being plus 4 cosine x, and then plus c. . Okay. Did I lose you? Any questions on that?
Could you explain how I just got lost when, so I understand why you did the 4x sine x equals a plus the integral of sine x times 4 dx, but then I'm lost in your next step in the math.
I just took the antiderivative. I just did the antiderivative of this one.
That's just the antiderivative? Okay.
Yeah, right? 4 sine x. What function has a derivative of 4 sine x?
Okay, and that's the antiderivative.
Antiderivative, right? So the idea of this undoing the product rule is this one we can't do with techniques that we know, but we can do this one. And that was the case.
Okay.
And then we just solve for the one we're asked to find indirectly. So it would be fg minus that.
Okay, and then the plus c just.
We'll always have so now we're not going through all the steps of a to the x sine t 4 dt. We're just going to skip all that, and just know that whenever you have an indefinite integral without limits, it means all possible net accumulation functions starting from all values of a.
Yeah.
And that this plus c will be the minus f of a or whatever.
Right. Thank you.
Yeah, sure. Okay, I want to start another example. We won't have time to finish it, but I'll post a video that finishes it, but I do want to get started, and then we'll take the quiz. All right, so here we go. So next one I want to do is the integral of x squared e to the 3x. So that's the one we're trying to find. Is it undoing the chain rule? All right, always the first question. Is it undoing the chain rule?
Yeah, in a way.
No.
How would we change this? How would a slight alteration to this so that undoing the chain rule would apply?
3x to the third.
Right. This would have to be cubed, x cubed. If x was cubed, then look, we have the derivative over here as the chain rule. So as long as that's an x cubed, we could do undoing the chain rule. But it's not an x cubed. We have a different problem than that. We can't do it. So we're going to try our technique here. And so f g prime. So we'll try x squared and e to the 3x for f and g prime, right? We'll just match them up this way. That means that f prime is 2x, g is e to the 3x, but then we also need
1/3.
1/3, right? It's just a little mini undoing the chain rule on that, right? So we need a 1/3 e to the 3x, thinking about the derivative of this to get e to the 3x. All right, so then that means, what is our g f prime? It is 1/3 e to the 3x times f prime 2x. And we know that fg is x squared times 1/3 e to the 3x. Okay, question. Is this doable now? Is this attainable by our known techniques? And the answer is no. Okay? This would, if it were undoing the chain rule, this would have to be 3x squared. If it were 3x squared, we'd be good, because then we could use undoing the chain rule. But we don't have that. So how can we do this?
Do it again.
Do it again, right? So we actually, it's not attainable yet, but it's closer, right? Because before we had x squared 3dx, e to the 3x. Now we have just x to the power 1. So maybe if we do it one more time, this will be constant and we'll be able to do it. So now we're going to take this and we're going to, on just that integral, we're going to use the same technique. We're going to have what? Capital F is going to be 2x to the first. I'm going to use capital F now and capital G. G prime is going to be 1/3 e to the 3x. And then we can find f prime is 2. And g is going to be e to the 3x again, but now this time 1/9. And so I'm doing this technique as a sub-problem within the bigger picture. I'm starting anyway. I'm not going to finish. We're going to call it there. And so you can watch me. I'll post a second video in today's video. This will just take another 5 or 10 minutes to finish this out, okay, in the video. And you can see how there's kind of like 2 layers here. We got the big picture problem where we're solving for this one. But when we get to this supposedly easier one, well, we need to use the technique again. Use the technique again.